This is a section 11.1, graphing square root functions. A radical function contains a radical expression, that means a square root sign, with a variable in the radicand, that is underneath the radical. Some examples of this would be y equals the cubed root of 2x, or y equals the square root of x plus 2. The most basic radical function we call the parent square root function, and that is y equals the square root of x. We're going to graph this now by making an input-output table. So I used values of x 0, 1, 4, and 9. To take the square root of x, y equals 0, 1, 2, and 3. The resulting graph is shown here with the red dots, which I will connect. Okay, so we're going to just draw it like this. The graph begins at 0, 0, and it trends upwards. Okay, you can see that the vertical increases tend to lessen as y increases. That means it's not going up as much vertically towards the end of the graph as it was at the beginning of the graph. Here's example 1. Graph y equals a times the square root of x. Let's try this one. Y equals 3 times the square root of x. We're going to find the domain and range and try comparing it to the parent function of y equals the square root of x. So the first step is to make an input-output table. I set values of x as 0, 1, 2, 3, and 4. If you wanted to use values that you can easily take square roots of, that would be fine. I calculated the value of y by taking the square root of the x value and multiplying by 3. So the values of y are 0, 3, 4.2, 5.2, and 6. In this case, the domain, or the x values, must be that x is greater than or equal to 0. Since x is underneath the radical, it cannot have a negative value. The lowest value it can have is 0. So x is greater than or equal to 0. The range is y is greater than or equal to 0, because if you look at the input-output table, when x is at its lowest value of 0, y is also 0. So the graph is all going to be in the first quadrant. The graph in blue is actually a vertical stretch of the parent function. So let's connect these lines. You can see that the new function follows the blue line, and the old function is going to follow the red line. Because we're multiplying the new function by 3, it becomes a vertical stretch of the old function. That means it increases at a much faster rate, and you can see how much more quickly this goes up. In example 2, we're going to graph y equals a times the square root of x when a is negative this time. So we're going to try y equals negative 0.5 times the square root of x, and we're going to compare that with the parent function. Again, I made an input-output table. You can take a look at those values. You can see because x is underneath the radical again, the domain of x must be greater than or equal to 0. The range as well is y is less than or equal to 0, though, because we're multiplying the x values by a negative value, by a negative 0.5, so the range is going to be less than 0 or negative each time. The graph is going to be a reflection of the original. Okay, that means it's going to go below the axis so that you can see it. And here, in this case, it's going to be the blue line is where I graphed it, just down here. And you can see the original follows the red points up in the first quadrant, so it's going to be this way. Now, if this graph were just negative the square root of x, it would be a perfect reflection, a perfect mirror image of the parent function. But since I multiplied it by negative 0.5 or negative 1/2, it's half as big. It's actually a vertical shrink and a reflection at the same time. You can see it's narrower and it flips into the next quadrant. take a look at these graphs of square root functions. So when we look at a being greater than 1, the graph is going to be a vertical stretch of the original. When the absolute value of a is less than 1 but greater than 0, the graph is a vertical shrink. That means you're multiplying by a fraction, so it's going to be narrower. When a is less than 0, the graph of a times the square root of x is going to be a reflection. It's going to be in a different quadrant. It's going to be like the mirror image that we saw when we were doing parabolas. In this next example, we're going to graph y equals the square root of x plus k. Adding k to the equation moves the graph up or down the y-axis. This is called a vertical translation. So we're going to make a table of values here. Now, please note that the 2 is not under the radical sign. It's outside and separate from the radical. So in our table of values, when x is 0, y is 2. When x is 1, y is 3, and so on down the line. The domain here is x is greater than or equal to 0. But you can see in this case, when x is 0, y is 2. So the range is y is greater than or equal to 2. The lowest value that y can be is 2. We're going to sketch the graph and compare it to the parent. You can see how the graph begins above the original. Remember, when x is 0, y is 2. So here, I'll switch colors here. This new graph is up here. What's key is that it's beginning at 2. Okay? The original follows the red dots down at the bottom. Okay? The red points that I've graphed already. I've left the parent here for you so you can compare it. Okay? It's basically the same shape, but what's happened is it shifted it up by 2. And that's what we're doing when we add 2 to the end underneath the radical. In example 4, we're going to subtract from x underneath the radical. So now this whole expression is underneath the square root symbol. It's y equals the square root of x minus h. Okay? So we're going to try y equals the square root of x minus 4 and make a table of values. The lowest value that x can be here is 4, because the lowest value you can have underneath the square root sign is 0. So x is going to range from 4 and upwards. When x is 4, y is 0. When x is 5, y is 1. Okay? What you're doing when you do this is you're shifting 4 to the right. This is called a horizontal translation of the parent function. The range here is y is greater than or equal to 0, because you can see the lowest value y is 0. But the domain is x is greater than or equal to 4, because the lowest value that x can be is 4. This is the horizontal translation in blue. Okay, so it's shifting. It's starting here at 4 rather than starting at the origin. Remember, the parent function always starts at the origin. So again, the parent function is in red. Okay, this horizontal translation is in blue. What the translation means is it is moving over by 4. Okay, so it's shifting over by 4, because the 4 was what was underneath the radical sign. Now here's the most complicated case. In this case, y equals x minus h plus k. The plus k is not underneath the radical sign, okay? Just the x minus h is, and the k is added at the end. We have to think, what is this doing to the function as compared to the parent? Well, we know that adding k is going to raise the function if it's positive and lower the function if it's negative. Remember, that shifts it up and down the y-axis. The negative h under the radical shifts it horizontally. Remember, we just talked about the horizontal translation. So we're going to take a look at this one. Y equals 2 times x plus 4. The x plus 4 is underneath the radical, and then minus 1. In this case, the h is -4 and the k is -1. Remember, the graph's going to shift based on those numbers, and they do two completely different things. I made a table of values here so that you could see. The lowest value that x can be is -4 because that puts a 0 underneath the radical. And when x is -4, y becomes -1. So here I plotted it so you can see. I'll try to keep the table of values there for you. Okay? And again, in blue, this is what we're looking at. Okay? That's the graph. So you have to take a look at that original equation and see why did that do that. All right? So make sure you understand the shifting back and forth, the shifting up and down, the changing so that it's vertical reflection, whether it's stretching it, whether it's shrinking it. The more you graph these, the more you'll understand what these numbers are doing.